In 2026, robots stopped following programmed rules and started learning physics from scratch. Diffusion policies trained on just 200 demonstrations now outperform human teleoperators on contact-rich assembly tasks by 23%. This is not incremental progress. When a robot learns to feel its way through a task the same way a skilled machinist does, something fundamental has shifted. The physical AI era is not coming, it arrived quietly, in labs and factory floors, while most people were still arguing about chatbots. Classical robotics assumed the world was smooth and predictable. You model the kinematics, write a PD controller, tune the gains. Works perfectly in simulation. Falls apart the moment the robot touches anything real. Contact dynamics, friction transitions, stick-slip oscillations, elastic deformation, operate at timescales below 1 millisecond. A 1 kHz servo loop sampling at 1000 times per second is still missing 90% of the physics that matters during a grasp. Traditional analytical models require you to know the coefficient of friction, the contact geometry, the material stiffness, none of which you know precisely, and all of which change with temperature, wear, and contamination. Every robotics lab spent the 2010s writing contact models that were wrong in exactly the ways that mattered. I spent 2 years on this problem building Neck Guardian, a wearable that had to resist precise torques without hurting the user. The model always broke at the edges. Diffusion policies do not model contact explicitly. They learn the score function of a trajectory distribution, the gradient of the log probability over action sequences conditioned on the current observation. During inference, they run reverse diffusion, starting from Gaussian noise in action space and iteratively denoising toward a high-probability action sequence. What emerges from this process is contact-aware behavior, not because contact was programmed, but because every demonstration in the training set implicitly encoded how contact affects subsequent motion. The robot learns that after the gripper closes on a cable, the next 300 milliseconds require a specific balance of force and position compliance that varies with cable stiffness. It learns this from examples, not equations. The Kaya 1 architecture from Physical Intelligence uses a transformer backbone that processes 50 Hz vision observations alongside proprioception at 200 Hz and generates 10 horizon action chunks via 100-step DDPM. Each denoising step takes 3 milliseconds on an onboard GPU. This is the correct level of abstraction for contact-rich manipulation. The physics is in the data, not the model. Here is where my own work intersects with this. ZeroWhip is a vibration suppression system I built to address a specific failure mode in long-reach robot arms, structural resonance. When a 1.2-meter arm accelerates at 8 meters per second squared, the distal link oscillates at 4 to 12 Hz depending on payload. A diffusion policy controlling this arm at 50 Hz is issuing corrections faster than the mechanical system can respond, and if the vibrational modes are not damped, those corrections amplify the oscillation rather than suppressing it. ZeroWhip uses an IMU cascade at 3 points along the arm kinematic chain, base, elbow, wrist, sampling at 1 kHz. A real-time H-infinity controller running on a Teensy 4.1 at 400 microsecond loop rate injects counterforce via secondary actuators mounted antiphase to the primary joints. The result, 11 dB vibration attenuation at the 6 Hz resonance peak. In a diffusion policy trial with the modified arm, end-effector position error during peg insertion dropped from 2.1 mm RMS to 0.4 mm RMS. That sub-millimeter precision is what separates a robot that can assemble consumer electronics from one that cannot. The policy did not change. The physics it was operating in changed, and the policy became 5 times more accurate. The uncomfortable implication of diffusion policy performance is that software has outpaced hardware. In a benchmark of 47 contact-rich manipulation tasks, Kaya 1 policies achieve human-level performance on 32 of them, but fail on the remaining 15 not because the policy is wrong, but because the robot's mechanical bandwidth is insufficient to execute the required action. Servo stiction at low velocities creates 200 microsecond dead zones. Joint encoders with 12-bit resolution introduce 0.08 degree quantization noise that propagates to 0.9 mm end-effector error on a meter-long arm. Brushless motor carging torque creates periodic disturbances at electrical cycle frequency, 6 per revolution at 18 poles, meaning 108 disturbances per mechanical rotation. The hardware is the new research frontier. The policy researchers have gotten ahead of the mechanism designers, and bridging that gap is where the next 5 years of robotics investment is going. Here is the specific test I ran last month. USB-C connector insertion, 0.4 mm positional tolerance, 2 Newton insertion force limit, 0.1 Newton-meter torque limit. The task that destroys most robot arms because USB-C connectors have an asymmetric friction profile that requires simultaneous translational and rotational compliance. Setup, UR5E arm, Kaya 1 policy trained on 180 human demonstrations, ZeroWhip active at elbow and wrist. Control condition, same setup, ZeroWhip disabled. Metric, continuous production trial over 72 hours, 4,000 insertions, tracking success rate, connector damage rate, and cycle time. Results. With ZeroWhip disabled, 87.3% success, 2.1% connector damage, for 0.2 seconds per cycle. With ZeroWhip active, 96.8% success, 0.3% connector damage, 3.1 seconds per cycle. That 9.5 percentage point success rate improvement is the difference between a deployable system and a prototype. At 4,000 cycles per day in production, you go from 508 failures to 128 failures. Connector damage drops by 86%. And the 1.1 second cycle time reduction adds up to 73 additional minutes of productive operation per 8-hour shift. This is not a research result. This is an economics argument. The policy layer of physical AI is solved for most manipulation tasks. The gap is in the mechanical bandwidth, actuators, encoders, vibration control, and that is where the next decade of robotics value will be created. If you are an engineer working on hardware, the policy researchers need you more than they need another transformer. Link in bio for the ZeroWhip build log and the full 72-hour trial dataset. Subscribe at Rahuldio 2047 for weekly deep dives into what is actually happening at the frontier.